Hello and welcome. Thank you for giving me the opportunity to talk here at this conference. My name is Conrad Freuling and I'm working at the British Loeffler Institute. We are a WHO collaborating center for rabies surveillance and research, and we also act as a VOA reference laboratory for rabies. Today I'm going to talk about high-resolution settlement layer, that is an open data set that can be used to estimate dog populations. So since about 10 years, we've been working in Namibia, and we faced the problem that for analyzing and planning dog vaccination campaigns, we are lacking of good quality dog population estimates. This is partly because it's a very segregated and dispersed human population in this part of Namibia, the northern communal areas. As you can see here on the left-hand side, it's very separated into individual homesteads, and normal mapping tools such as OpenStreetMap do not provide the desired resolution to plan dog vaccination programs. Also, for evaluation, cumulative datasets may be available based on the lowest administrative level, that is constituencies, but because of the size of Namibia, these constituencies are really large and also are not very helpful for planning and evaluating your dog vaccination campaign. What you can use is gridded data set. That means that the population is based on individual tiles at different sizes. So what we used in the past is open source data, gridded population of the world with a grid cell length of 1 by 1 kilometer. And that can also be used to estimate the vaccination coverage, but it has a low resolution for planning. One option that has become available in recent years is Facebook or Meta Data for Good. What they did is they analyzed satellite images and identified houses and put to each and every house on a tile length of 30 meters the human population. So this is available at the Humanitarian Data Exchange and is available for every single country. In the past, it was available as a GeoTIFF file, but is now available as a CSF file. So it can be used for any GIS tools. This is what it looks like for Namibia. You can see here on the left-hand side the normal satellite images, and the red dots display identified houses based on the metadata for good. This is an enlargement, and you see how accurate it is. It identified quite well these households. So this is what it looks like in more urbanized areas. Again, it has a 30 by 30 meter square length, and for each point there would be a data set for the number of people living on that individual place. What you can do now is to count these cells with populated with human population and identify the number of grid cells. We used OpenGIS tools like QGIS for this analysis. What we then did is we structured the dog population. We multiplied the human density with a factor. In rural, remote areas, we used the factor of 0.24. That means there's a dog-to-human ratio of 1 and 4. And in urban areas, we used a dog-to-human ratio of 1 in 10. In total, we came up to 40,000 dogs in that area, and that matches quite well the results that we obtained previously with a KP study. We then used data from areas where we went to during the KP study to see how well our approach matches with the results of actual surveys. And you see that on the left-hand side. In urban areas and in rural areas, it works quite well. In urban better than in rural, but that's a problem of identifying these homesteads in the rural area that is more difficult for KI to identify these houses. So what we then did, we used all the data and compiled a dog population sort of structure for this area. You see that the majority of people live in rural, dense areas close to the cities, as opposed to the dog population. The majority of dog population live in rural, remote areas. And you see here on the right-hand side the human population and the respective dog population also stratified for the individual constituencies. What you can then do is you can make nice maps out of this data to make a dog population density map, and that has been published on bioarchives. And the average dog population density per square kilometer was 8 dogs per square kilometer, but you had areas that went up to 500 dogs per square kilometer in these urban, densely populated areas. What we then did, we used these data sets and tried to optimize vaccination campaigns. In the past, it was tradition to vaccinate dogs also at crush pens, these cattle vaccination posts in this area. And we asked the question whether it would be more beneficial to move these vaccination points closer to schools, to combine schools and crush pen vaccination, or to shift vaccinations to medical centers and vaccination points. We assumed then a compliance to vaccination as a function of distance, meaning that close to the vaccination point, between 0 and 1 kilometer, there would be a high compliance of 90% to bring the dogs, versus 5 to 10 kilometer distance to the vaccination points would be as low as 5%. Using all this information we compiled, we came to the following conclusion. Using crush pens only, we would reach only 44% of the dog population, as opposed to schools where we could reach 61%. The combination of schools and crush pens, because of this overlap of the only goes to up to 65%, meaning it becomes extremely difficult to reach the 70% threshold of vaccination coverage. If you switch to vaccination sites at health facilities, only 50% of dogs will be vaccinated. We also use the data to calculate the cost per dog vaccinated. I will not go into detail, you can look it up in the publication, but the costs are quite high because of the logistics, and it ranges between $6.30 and almost $7, depending on the calculation method, and that is quite in the range of what has been published before, especially for Tanzania, where there were also high logistic costs. We also use published data from Blantyre, from Mission Rabies, to see whether our approach is applicable to other places in Africa. And here we came close to 4% to what people from Mission Rabies were actually estimating on the ground based on their vaccination coverage, as opposed to literature if you use a 1 in 20 dog to human population estimate. Again, if you use other methods of dog population estimates, as was shown by Katie Hampson's group in Tanzania, the estimates are ranging quite massively, and we have the feeling that using this remote sensing and remote estimation of dog population, provided you have some rough estimates of the dog to human ratio, provides a much better estimate than using these highly laborious and expensive surveys that you have to do to come up with highly detailed mapping. The best, or one of the best things about these population maps is the detail. You can see it here for the Zambezi region in Namibia, where we did an oral rabies vaccination trial last year. Each dot represents a household, and so you can focus your areas of activities close to where the people are living. Early in the morning, we went into the suburbs of Katima Mulilo, the capital of the Zambezi region, and vaccinated dogs in these formal and informal settlement areas. And during 4 days, we vaccinated almost 1,000 dogs in these areas. And then during the day, we went along the streets, and whenever we saw dogs, we approached them and vaccinated them during day 1, day 2, day 3, day 4, and in total we had 2,343 dogs vaccinated in these areas. Again, we used our approach. We put a layer on top of it and calculated the number of dogs per layer, and then counted the number of dogs vaccinated and came up with the vaccination coverage. So we did not do a post-vaccination survey, which would be extremely challenging, especially for oral rabies vaccination, and came up with a nice estimate of the vaccination coverage, which was on average 30% vaccinating dogs, but it was only a demonstration project. So the result was very promising. We had 93% bait acceptance in rural areas and 83% in urban areas. In urban areas, dogs were a little bit more scared of us driving around in this area and approaching them with baits. In rural areas, they were much more fond of these baits and were seeing that as a proper food. You see here on the left-hand side the effectiveness of our method. In urban areas, we vaccinated more than 25 dogs per hour per team, and in rural areas was 22 dogs per hour per team. In rural areas, it was based on a lot of driving. You see that here from point to point to point. We were driving along in these villages from homestead to homestead, and we covered almost 1,000 kilometers per team during these 4 days. So 250 kilometers per day we're just driving under hard conditions. But still, we were much more effective than previously in central point vaccination in the Oshana region, where they only vaccinated 11 dogs per team per hour. So the results have been published in One Health, and one of the main findings is that because it is so much more effective and you can reach more dogs in a shorter period of time, even though the bait and vaccine itself is more expensive, the total campaign costs are reduced as compared to parenteral vaccination if you are more efficient. And this will be a game changer in approaching dogs in many parts of the world. So in the past, we've been involved in developing this program of oral rabies vaccination that starts from safety, immunogenicity, efficacy, and we're now at the stage of effectiveness in the field where we contributed our studies in Namibia. With this, I'd like to thank all of our colleagues in Namibia, the funding organization at our Ministry of Food and Agriculture and Ministry of Economic Cooperation and Development, VOA for organizing everything and being the project partner, and also colleagues at FLI who helped us, and Mission Rabies for using their mobile application tools. Thank you for your attention, and I'm happy to take any questions. Thank you.